I have the habit of recording the lectures. In the past, haven't really done anything with them, but maybe this time, I'm going to see how much trouble it is to put them online after class.
Like on Sakai?
Not on Sakai. I think they will. It's not so easy to upload a large file to Sakai, but I'll put it on a website and then send you guys the link. But let me see how much trouble it is to do that, because it's too much trouble and I can't do it. Okay, so before we get started, there's a couple of new people here. Those of you who weren't here last time, can you tell me who you are? Yes, please raise your hands and let me write down information. Yes?
Nadia.
Nadia, okay. Nadia. And your last name was?
Kirsch, A-I-R-S.
And then Eunice?
Evelyn.
Evelyn?
Gonzalez.
It's under Lisa, but I go by Ellie, and last
You
name.
like Ellie?
Yeah, and last name Taylor.
Yes.
Ruchika, last name Majumdar.
Sachin Taneja,
How do you spell your first name?
Sachit,
And your last?
Taneja.
Okay. So my name is Winston. Okay. Welcome to the class. Okay, so today we're going to start off with just some very basic stuff. A lot of notation that you've probably seen before. I'd say that most of this first chapter is probably some sort of review or reconstruction of the material that you've seen before. Okay, so chapter 1 is the basics. So I'm going to start off with some notation. And this notation is due to a person called Bourbaki. So the Bourbaki notation. So one uses a bold script, Blackboard bold script N to denote the natural numbers. So this denotes the natural numbers. And for most people, that means the numbers 1, 2, 3, 4, 5, 6, 7, 8, 10, etc., etc. Okay, so the whole, the positive whole numbers. Okay. Then one uses a bold script Z to denote the integers. Okay. And who knows what the integers are? What are the integers? Yes, Rachel?
Positive and negative numbers.
Yeah, positive and negative natural numbers, and 0, you don't include that in either group. So let's say 0, 1, negative 1, 2, negative 2, 3, negative 3, etc., etc. Right? So it's the integers, right? I should say that some people count 0 in the natural numbers. Most people, I think, start the natural numbers from 1. Then there's Q, the rational numbers.
Just normal Q? Normal Q or like bold?
Bold Q. They're all going to be bold. Yeah. So this is, as a Blackboard bold is basically what you'd like to do if you had a bold font. If you could do a bold font on the Blackboard, but you can't do it efficiently, right? So maybe you could do some sort of bold, but it would take too much time. And so the shorthand for bold is to just put a vertical line through everything, or like double some lines. Okay, so that's the Blackboard bold font. You can find it. It's sort of strange, but you can find it in print fonts. So you can print in Blackboard bold font, and mathematicians do. So you'll see it in math papers. Okay, so rational numbers. Who can tell me what the rational numbers are? What are rational numbers? Who remembers what the rational numbers are? Nobody.
Fractions?
Fractions, okay, so fractions is things that look like P over Q, where P and Q are what? Can they be anything?
Q cannot equal 0.
Q is not equal to 0, right? And what are P and Q? Are they, P and Q are they just any numbers? Can I put
Integers.
they're integers? Okay, so P and Q are integers, and Q is non-zero. Right. So if I have something, right, if I have something that can be reduced to this form. Does anybody confused by that? And then there is this thing. So rational, right, means like a ratio. Like this rational numbers means a ratio. You have quotient. The Q stands for quotient. All these things mean the same thing. Some ratio, fractional. R is the real numbers. And we're not really going to define the real numbers, but we're just going to say that they're all things that can be expressed in decimal form, which is a sort of circular definition if you think about it. It's a bad definition, but we're not going to define what the real numbers are because it's a little bit tricky to do. Okay. Each of these things is a little bit better than the one preceding. You think about, you have the rational numbers, you have the natural numbers, and then you have the integers. Well, in the integers, right, you can have, you can have, for example, if you had only natural numbers and you said, what's 2 minus 3? Well, like if I ask my daughter, what's 2 minus 3? She's 6, right? She says, I don't know, because she doesn't know, her number system hasn't expanded to include this, right? So here you have, there's an answer to that, to that question here, right? Or another way of saying that is that, and then here, you can say, you can divide, right? Now, what's the difference between the real numbers and the rational numbers? What the real numbers do for us that the rational numbers, what can we do in the real numbers that we can't do in the rational numbers?
We can have numbers like pi that you can't write as a fraction.
Yeah, so there are some numbers. So, the rational numbers are the numbers that can be written in this form, right? Numbers that can be written as a fraction of where the top and bottom are integers, and the bottom is non-zero. Okay, but it turns out, and this is sort of a surprise, that there are some numbers that can't be written that way, right? Maybe when you're a kid, you think, oh, all numbers, basically all numbers can be expressed as one integer or another integer, right? But then it turns out, and this is never really explained to you, that there are some other numbers, the irrational numbers, and you throw those guys in, and then you have the real numbers. Okay, so pi, for example, is something that is a real number, but it's not in the rationals. So this notation means it's in the reals, but not in here. So this excluding the rationals. Right? Pi is in the reals, excluding the rationals. Right? So it's an irrational number. Yes, Cynthia.
And would decimals go in the integers section? Or the
So,
irrational?
well, it sort of depends. So, like, if you give me an example of a decimal, like if I say like 0.12, right? Well, that's not a natural number, that's not an integer. Is that a rational number?
Yes.
Yeah, sure. Why? How do you express it as a quotient of integers? Right, you can write this as what? 12 over 100, right? 12 over 100, that's fine. 6 over 50, 3 over 25, right? Whatever. Those are all fine expressions for it. It's rational, right? If I have something like 0.12, 12, 12, 12, 12, 12 repeating, right? Where does that belong?
Real numbers, but rational.
It's also rational.
Okay, so some people are saying, who says that this is rational? This is a rational number, it can be expressed as a ratio. Who says it's an irrational number? It cannot be expressed as a ratio. So actually this can be expressed as a ratio. In fact, there's a fact that I'm just going to give it to you. We're not going to explain it. Yeah, we're not going to explain it for now, at least. We could explain it, but I'm not going to explain it. Okay, so rational numbers. So the rational numbers are those which have. So I'm just going to put this as a fact, but we could explain it. Rational numbers are those which have repeating decimal expansions. Decimal expansions. Okay, so if you see something that has a repeating decimal expansion, right, then you know it's rational. And if you see a rational number, you know that when you divide it out, if you see a rational number, you know that if you divide it out, it will have a repeating decimal expansion. You may be wondering, where is the repeating decimal for this first example? It's the zeros, right? You have a repeating. This actually does have a repeating decimal expansion. It starts repeating after the 2. Yeah. So, can anyone give me another example of what they think is an irrational? So, Rachel said, well, pi is an irrational number. What's another example? Not
Yeah, square root of 2.
Square root of 2. Square root of 2. Another famous irrational number. So, another guy that is real but not rational. Right. So, lots of these square roots, as long if they're not perfect squares, often are in fact are always irrational numbers. At this point, we could say, how do you know? Right. You could ask, how do you know this? Right? How do you know that these things cannot be expressed as irrational? How do you know that these cannot be expressed as ratios? Right? How do you know that the square root of 2 cannot be expressed as a ratio? Simply.
Well, because if you even try to put it in like fractional form, I guess like it would be 2 to the 1/2, and that's still not a ratio, I guess.
So the question is, how do you know that there's no ratio that works for this? Right? There's no. So what we're saying is that there is no pair of integers, pair of p and q there is no pair of integers so that p over q equals 2, or p over 2 squared, equals 2. Right? That's what we're saying. Yeah.
Can't you get like really, really close, but you can't, it's like infinite numbers. It would be like 1 point something, like blah, 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 right?
Yeah.
And aren't they like still trying to, like, there's like computers that are like getting all the values of like pi and they're still.
That's right. So it's sort of a game to show computer processing power, or to show the efficiency of your calculation techniques. People say, we've calculated pi to 1 billion digits. Of course, and the thing is that since pi is irrational, then it will never, it doesn't have a repeating decimal expansion, right? Even if you know it to 1 billion digits, you still have an infinite way to go, right? You still don't know, there's still an infinity of stuff you don't know about the number. You can, for irrational numbers, you can't write them down. You can only write down 0% of them.
When they calculated pi though, isn't that like some equation to find pi? Like, isn't there some way to express it exactly? Like, I don't know how they got it, but it's like this circle.
It's the diameter of the
So certainly that's the definition of pi, right? The definition of pi is the ratio of the circumference of a circle to its diameter, right? So that's what it is. But one calculates it by trapping it basically between 2 other numbers, and you try to make those 2 other numbers as tight as possible, right? Within 1 billion of 1 billion digits typed. Yeah. Anyway, so all I want to say now is that we could, at this point, you could say, well, how do you know, if we're thinking in terms of the skeptical child again, if you said, like, how do you know that that's an irrational number? We'd actually have to defend it. And I'll tell you a little story. So the Pythagoreans, 2,500 years ago in Greece, initially, their number system was, they thought of numbers just as ratios. Okay. They thought of numbers as ratios, and the story goes that their whole system, their whole world system was based on this idea that everything was ratio, right? That there was some ratio of the orbits of the planets in the heavens. There's something called the music of the spheres, right? Music is based on ratio, right? If you take a string and you cut it in half, you get an octave, right? You get a note an octave higher. If you take a string and you cut it in thirds, you get something that is an octave and fifth higher, right? Et cetera, et cetera. So for them, ratio explained everything. It was almost a whole, the fact that number was ratio and the world was ratio was almost a holy thing for them. And it said that, so they started wondering, what about if this is 1 and this is 1, what is this thing? And what is the ratio that expresses this? Well, we know this is actually the square root of 2, right, which is an irrational number. And so it said that the person who figured out that this was an irrational number, that by him figuring this out, it so shocked them that they immediately killed him. That's the story. In fact, that's probably not even the right story. It's probably, I feel like I heard that story. Okay, it's in the book. It's probably not. Don't talk to the historian about it. Anyway, but there's in one of Plato's books, it's called the Timaeus. And this I'm not sure of either, but I'm going to say it anyway. Again, I'm going to say it anyway. It said that in this book, Plato says, he is, and I'm going to phrase it in a way appropriate for scripts. She is not worthy for the word. She is not worthy of the name of woman who does not understand why the square root of 2 is irrational. So maybe if we have time at the end of the class, I'll give the argument that the guy who I claim was thrown off the boat gave to show that it was irrational. Okay? It won't take that long. It'll take maybe 5 minutes. Maybe 5 minutes or so. Okay. Enough jabbering for now. Okay. So numbers, right? Those things are numbers. There are more numbers than that. Those of you, past the real numbers, there's these things called complex numbers. Right? You call them the complex numbers. There are also other numbers, other systems. There are these things called periodic numbers. There are things called surreal numbers. There are other things. But even I don't know what they are. I just know the names. I forgot what they are. I knew it one point, but I forgot. Okay, other things that will be sort of basic. Segmentation, which we've already started to use, in fact. You have something like this. So I'll just give an example. If I say S equals something like this, right? So this is an example of segmentation, and in English you read this as S is the set of X in the reals, X in the real numbers, such that X squared is less than 2. X is the set of X, which are real numbers, such that that x squared is less than 2. Such that is sort of an old-fashioned expression that mathematicians still use. It means like with the property that, x squared is less than 2. Right. I'm hoping that you've all seen this sort of thing, seen this sort of thing before. One thing that we've already sort of been using is this thing is an element of, right? This thing means is an element of, right? Is a member of. So if I say like, if I say that 1 is a member of S, like 1 is an element of S, that's true, right? Because 1 is a real number whose square is less than 2, right? 1 is an element of S, it's true. For example. Right? Another example, if I say something like the set of real numbers such that the absolute value of x minus 2 is less than or equal to 3. I hope you can is everybody able to read this sort of thing? This vertical bar is the such that, right? Is the such that mark, right? X, so the set of x which are real numbers such that the absolute value of x minus 2 is less than or equal to 3. So this is set notation. Right, what is this set? Can anyone tell me what this set is? Or think about it for 10 seconds, and then tell me what this set is. Suki.
Negative infinity to 5.
Negative infinity to 5. Okay, so here's-
Oh, I didn't.
So everything from here up to 5 inclusive or not inclusive?
Inclusive.
It sounds like you were changing your answer.
Well, I forgot absolute value.
The absolute value,
Yeah.
okay, so yeah. So, yeah, that's the absolute value. Is the absolute value of Ruchika?
X can be greater or equal to -1, but less than or equal to 5.
Okay. X is greater than, here's -1, here's 5. And you're saying it's like this. Other answers? Okay, so this is something you've probably seen before. That's right. Just to remind you what the absolute value is. The absolute value, this is pretty important, actually really important in this class. What's the absolute value? So here's the definition. The absolute value of x is, we define the absolute value of x as x if x is greater than or equal to 0, and as negative x if x is less than 0. Right? So let me just read this to you. Right? The absolute value, of x, and then this mark means is defined to be. If I have a colon and an equal sign, it means is defined to be. This thing on the left is defined to be that thing on the right. Is defined as. And then there's like a conditional statement here. It's defined as x if x is positive, right? So if you give this function, you know, if you give it like a 5, it'll give you back a 5, right? Because it'll say, oh, the number is positive, I'm going to give you back what you handed to me, right? And then if the number is negative, if you give it a -5, it'll look at it and say, oh, you gave me a -5, I'm going to give you back negative what you gave to me. So I'll give you back negative -5, right? So absolute value of -5 is of course negative -5. Absolute this is just instructions to the machine, right? The machine says, you handed something, and then it says, oh, is it positive? Oh, I'll just give it back. If it's a negative, I'll give you back the negative of what you had. Yes, that's it.
Could you do an example with the number line?
Yeah, sure. So, for example, if I say, let's see, okay, here's an example. Suppose I say, what's the set of x, because the absolute value of x is bigger than 1. What's the set? Tell me what the set is of things which are bigger than, whose absolute value is bigger than 1. Yeah, not fine.
X would be less than -1 or greater than 1.
Less than -1 or greater than 1. And probably the way you just sort of thought about it and just realized that that's what it was, right? If you wanted to use this definition, suppose you wanted to use this definition to see that, you'd say, well, okay, if x is positive, so you have to sort of break it into cases. Okay, let me do it sort of more geometrically. So you'd say, okay, so if I'm thinking about the positive numbers, right, then if I'm thinking about the positive numbers, then the absolute value of x is just x, right? For positive numbers, right? For positive numbers, the absolute value of x is just x, right? So you'd say, so for positive numbers, so for x greater than or equal to 0, this thing just means x is bigger than 1, right? Because if you're positive, then the absolute value of x is just x, right? So this becomes this, okay? And so for positive numbers, we have these guys over here, right? Okay. For negative numbers, so for x less than 0, what does this mean? The absolute value of x is bigger than 1. But what does that mean for a negative number? Well, the absolute value of x is which guy?
Oh, it just means that x has to be less than -1.
Yeah, let me slow it. Let me do it in even smaller bits. Absolute value of x is what? Sorry, say it again. If x is negative, if x is less than 0, then the absolute value of x is negative x, right? So we just put in the negative x here. Right? Negative x is bigger than 1. Right? This means negative x is bigger than 1. Right? In other words, x is less than negative 1. Okay? Multiplying both sides by -1, and you get this, and you get this times 1. Right? So just, I mean, that's sort of a pedantic way of doing what you sort of, you probably could just look at this and know what the answer is. But if you wanted to go through the definition, then this is how you do it. Does this make sense? I think I've taken something very simple and I've explained it in a complicated way. But this is sort of what you have. This is sort of the thinking that you have to go through to do more complicated things. Okay. Yeah. So please make sure that this makes sense. I'm sorry for that.
It's okay. Evelyn?
Evelyn, yes.
Can you explain inclusive and exclusive? Is that what you said?
Yeah. So if we say something like x less than or equal to 1, then that would be here's 1, that would be all the points less than 1 and including 1.
Okay.
So that's what we call inclusive. If it were like x less than 1, then that you'd say everything up to, but not including 1, so excluding 1. So I'm not sure if that was that helpful, Suki?
Yeah, thank you very much.
I'm just gonna keep on going anyway. Help or not. Something will stick. If I throw enough at you, something will stick on. Okay. Yeah. So So let me. So, so in general, for a positive, x, the absolute value that's being greater than a, absolute value that's being less than a means that, let's say that here's 0 and here's a, here's negative a. Right? For the absolute value that's to be less than a, just means that they lie between here and here. Right? The absolute value that's being less than something means that the size is smaller than a. And the absolute value greater than a means, as we just saw an example, this is a minus a, then you're either over here or you're over here. Right. Which is, again, stuff that I think you've seen before. Do these two statements make sense to everybody? If not, I can explain them in at least one way for now. Let me put up something that you might not be that familiar with. Consider if we have in fact, if x and y are real numbers, then the distance between x and y, which I'm going to write d of xy, is actually the absolute value of the difference. The absolute value of the difference. So, for example, if I'm looking at 5 and 3, right? The distance between 5 and 3. Well, you know that's 2, right? It's the absolute value of 5 minus 3. That's 2. The distance between, say, negative 3 and 5. Well, if we look at the absolute value of negative 3 minus 5, we get the absolute value of minus 8. That's 8, right? That's 8. Right. So if you take the if you have two numbers and you take their difference, and you take the absolute value of the difference, that gives you like the distance between the two numbers. I think that makes sense, just pictorially, right? If you take the difference between two numbers, you get some sort of length, but it could be negative, right? And you apply the absolute value to it, and you get the distance between here and here is the absolute value of a minus b, or the absolute value of b minus a, whichever. That's the same thing. So if we go back to our first example, we had something like this. The set of x real numbers such that absolute value of x minus 2 is less than 3, less than or equal to 3. Which Ruchika figured out for us. But now let's look at it from the point of view of distance. Okay, let's Let's look at it from the point of view of distance. If we write this in English in the sense of using the notion of distance, what this says is the points x whose distance from 2 is less than or equal to 3. Right? What we just said was that the absolute value of a difference is the distance between two numbers. The absolute value of a difference is the distance between the two numbers. Right? So here, what's it saying? That we're looking at the points such that the distance of x, we want x, whose distance, so the distance of x from 2 is less than or equal to 3. Right. The distance of x from 2 is less than or equal to 3, and then it's trivial, right? You say, okay, here's 2, and I want to be at most 3 units away, right? So here's -1 and here's 1, and I'm allowed to be at most 3 units away, right? So that gives it to you instantly. So this is a very useful interpretation of the absolute value. Very useful interpretation. To think of a difference, the absolute value of a difference, I'm going to write it in English, the absolute value of a difference is the distance between the 2 points. The absolute value of the difference is the distance between those 2 points. I actually like to think of things in this way. So, for example, going back to our second example, we were looking at x whose absolute value is greater than 1, right? Which you could work out using the definition, but that was sort of complicated. Right? Rather than using the definition, let's think of it like this. I'm going to think of this as x minus 0. I'm going to think of the absolute value of x as absolute value of x minus 0. That's okay. I haven't changed anything. That's 0. So now, in terms of distance, what's this? What's this? What is this thing here? Yeah, that's it here.
The distance of 0 is greater than 1.
The distance to 0 must be greater than 1. Right? So here is 0, here is 0, and the distance to 0 must be greater than 1. So we have to be outside here, and outside, we have to be at least this far away. Right? The distance to 0 must be greater than 1. We can't be inside this radius. Okay? So you just, in this case, using the geometric interpretation of the absolute value, you can make these sorts of things down very quickly. Now, sometimes you can't. Sometimes it's so complicated that you have to use the algebraic and long, sort of really tricky way of doing things. But often you can use this trick. Any questions?
What if you have on this other example toward the bottom of the board, you have x plus 2 is less than or equal to 3?
Yeah. So then what is that? So if I have x plus 2 is less than or equal to 3. Thank you for asking. That's a good question. That's great. Thank you. So what if I said, I really don't want to think about this algebraically. I'd really rather like to think about this geometrically as a distance. I can think of this as a distance too. Right? How would I go about doing so? Everybody except for Rachel. You're banned from speaking. and I should say now that you should think of that as an honor, like banned from speaking. In past classes, generally people are pretty proud that they participated so much that they've been. Yes, Leah.
Are you allowed to multiply both sides by a negative?
Well,
Fill the sign and everything? Or is that not?
you could, but that doesn't get you close into the notion of, to the thing of distance, to the concept of distance.
Do x minus minus 2.
X minus minus 2. Yeah, so this is the same thing as x minus minus 2, right? So this is the distance of x from -2 x plus is really a line. It really actually is a distance, right? It says that the distance from minus 2 must be less than or equal to 3. Right? So that is, we lie between here and here. The distance to minus 2 must be less than equal. So yeah, often it can be rephrased. And it may well be that by multiplying, in this case it didn't work, but sometimes some trick like that will be helpful. Okay. So now I think let me show you an example where I think using the geometric interpolation is not helpful, and unfortunately one has to go through the algebraic way. So get ready for this will probably disgust you. Or it may bore you. So here's an example from the text. I think this is from the text. Let's figure out what are the numbers such that 3x minus 2 over the absolute value of x plus 1 is greater than 1. So it's sort of hopeless. Right? 3x minus 2 is greater than the distance of x from negative 1. Maybe you could say that, but it probably would not help you to say that. Even if you said it, doesn't do it. So in this case, we're going to use the we'll use the algebraic. So recall x plus 1. The meaning of x plus 1. We're going to use the algebraic definition. So x plus 1 in absolute value is just going to be x plus 1, right? If x plus 1 is bigger than 0. And it's going to be negative x minus 1 if x plus 1 is less than 0. Right? In other words, if x is bigger than negative 1, or x is less than negative 1. Right? Okay. So that is, the meaning of the absolute value is going to differ depending on where you are. Okay. So what one has to do is just break this up into two possibilities. So let's suppose here's case 1. There are two possibilities. Okay. Case 1, x is bigger than or equal to 1. And actually, let me say x is bigger than negative 1, because if x is equal to negative 1, we run into trouble, right? If x is equal to negative 1, this thing blows up anyway. So we don't. That's not an option, basically. So notice x cannot be negative 1. So there are actually three possibilities, but there are two main ones. X is either bigger than negative 1 or it's less than negative 1. And then there's this third option, which we dispose of from the beginning. Okay, so in this case, if we are on the right side of negative 1, then then we're looking at this, right? We're looking at this, but we can get rid of the absolute value signs. Then the inequality reduces to this. Right? Because if we're on the right of negative 1, then the absolute value, we can just pull off the absolute value. Everyone. Is it okay?
Yeah.
Anyone confused? So we're trying to look at this inequality and find out where it's true. We're trying to look at this inequality and find out where it's true. And it turns out we'll break our world into two parts and say, okay, right now let's suppose that we're on the right side of -1. In that case, our inequality turns into this inequality, right? Because the absolute values just pull off. Right? If x is bigger than -1, then this thing is positive. We've fed the absolute value a positive number, and you just pull off the absolute values. Right? If x is bigger than -1, then this thing is positive. Right? So you can pull off the absolute values. Right? Because the absolute value, that's how it is. Okay? Okay, and so let's go on from here. We work it out. What do we do to solve this inequality now? Okay, and then? Somebody just tell me, Elizabeth?
Yeah.
Add 2 to that side. Okay, so 3x greater than x plus 3. 2x is greater than 3. X must be greater than 3x. Okay. So in this part of the world, these guys will work. In this part of the world, these guys will work. So we have some solutions already, right? We've divided the world into 2 parts, and in this part of the world, on the right side of -1, everybody above 3/2 is good. Okay, so these guys are good. These guys are solutions, and now let's do the other half, right? 3x minus 2, and so what should I write on the bottom here? What should I write on the bottom? 1%. No idea what you said. Positive, negative, 1%, 1%. Alexandra?
Yeah, Alex.
Alex.
Negative x minus 1.
Negative x minus 1. Okay. And then what do?
You multiply negative x minus 1 on both sides.
Okay. Do I have to worry about changing the sign? No, because I'm smaller than -1. I take negative x, that makes me bigger than +1, and I subtract 1, I'm still bigger than 0. If you think about it without going crazy, then it'll be okay. Anyway, this is positive. Okay, and then you just work it out as before, right? So you get add this thing over there, so you get 4x is bigger than 1. X must be greater than 4. X must be greater than 4. Okay, so that says that on the left part of -1, in this part of the world, you must be greater than 1/4. On the left part, for numbers that are less than -1, you have to be greater than 1/4. In other words, you have to be, for numbers that are less than -1, the only ones that work are bigger than 1/4.
A 1. -1.
For the numbers over here, you must be bigger than 1/4. In other words, there's no solutions, right? So there's no solutions over here. Okay, so putting it all together, we say, okay, at -1, there's no solution. For numbers less than -1, there's no solution. And for numbers bigger than -1, these guys work. So these guys are, these are the solutions, right? So just a second, Rachel. Solution set is x must be bigger than 3x. Yeah, Rachel.
Can you remind me when you have to switch the sign when you're like working on inequalities? Like
When you multiply by a negative number.
Okay.
So if you know it, if I had something like negative x is bigger than 3, right? If I multiply both sides by -1, then you have to switch the sign. Yeah. So anytime you multiply by a negative number, fortunately for us, this thing is not a negative number as long as x is the same. Yes, Evan?
Whenever we have the absolute value, we have to go through the 2 cases to see what works.
I'm afraid so, yeah. if it's this complicated, then this, I mean, you might be able to, who knows? Maybe there's some shortcut that you don't have to do this. But this is one way to do it, and this way will work.
And is it only when it's a fraction and absolute value on the bottom, or just in general if there's an absolute value?
In general, if there's an absolute value, this case splitting into cases, because the absolute value is defined in cases. Yeah, so you have to get rid of it, unless you see some more other way using geometry. Okay, that's it for today. Please turn in your diagnostics. Maybe pass them over to the right and pass them